you everybody for joining us this morning. Good morning, good afternoon, wherever you are in the world. A pleasure for myself and Andy Godley to be asked to give a little seminar on metering, which is a subject that we are very, very passionate about, and hopefully that will come across. Before we start, just a really big thank you to kind of Stuart and to Gary and the whole IWA team. I've watched a number of these webinars, I've watched a few on YouTube, and they've been absolutely brilliant. And I'm hoping that we don't do anything to ruin that standard. That they've been absolutely excellent in helping understand about leakage, about water loss, about non-revenue water, and a lot of the enablers. And so today we're going to talk about one of the enablers, which is metering. Andy Godley, he's a flow expert. He's been involved in flow measurement for almost 35 years now. And over 30 of those years have been at the Water Research Centre, so WRC, which is based in Swindon, which is about 70 to 80 miles west of central London. I work for Severn Trent Water, which is England's second largest water utility company, biggest water utility company. We're based in Coventry, which is about 100 miles north of London. Okay, so Andy's got control of the slides today, so you'll occasionally hear me say, Andy, let's go on to the next slide. So Andy, let's go on to the next slide. This is what we're going to be covering today. We're going to primarily look at DMA meters, because obviously they have a real impact for countries that have got DMAs and DMAs set up. And then we're going to look primarily at larger diameter meters. Gosh, there's a spelling mistake already there in the first slide. And these are large meters that have an impact on transmission mains and often on your system input volume meters on there. So we just move on to the next slide, Andy. Throughout the network, metering is really key. It's key that we know how much we abstract, but from a water loss point of view, it's important that we know how much is going into the system. System input volume meters, or sometimes in England known as distribution input meters. And then obviously we have metering throughout the network. Sometimes we meter large commercial users. We have lots of domestic properties that are metered, and obviously we have DMA meters and meters on the transmission mains. And often meters play an important role, or they do play an important role in pressured areas for PRVs. So throughout the network, metering is a real key enabler in letting us know where the water's going, and so we can do a water balance. Okay, we go on to the next slide, Andy.
Okay. So because, as Michael says, meters are critical to so many parts of the water network. Our entire management of water, the water network, flows around the network, and particularly leakage, eventually goes down to meters and the data we get from meters. And we know that there are a lot of things that can affect the accuracy of our meters. And we really want our meters to be as accurate as possible. But when they're in service, when they're installed, there are an awful lot of things that can affect the performance of those meters. And this is becoming more important, particularly as we start to look for smaller leaks, or we try and find leaks more quickly as they break out, or we're moving into the world of smart networks where we're integrating data from many meters. Having an understanding of the meter's accuracy, its installed accuracy, is absolutely fundamental. And there are lots of things that can affect that. And we're going to talk about some of these during the course of today. So I'm not going to go through these in great detail because we'll pick up on some of these later on. The line at the bottom there in green, telemetry, usually we have a meter that's sitting in a pipe somewhere, and that will be connected to a control system, to a SCADA system, to a logger, all kinds of things through the chain of telemetry from that meter. And it's very important that we also include the telemetry aspects in our considerations of what can go wrong, what can lead to poor data. And that's not something we're going to go into today because it is a whole, probably a whole presentation in itself. But just to give some examples, we've worked with a company that's done a survey of a lot of its larger meters and found an average of about 1.95% difference between what it's showing actually at the meter and what it's showing at its sort of downstream SCADA system. And that's not unique to the water industry. There's been similar studies in the mining industry as well. where they're showing discrepancies of sort of 2-3% between what's happening at the meter and then what's showing on control systems. So telemetry is something that you need to take into account, as well as all these various other things. So you saw on the list there something about hydraulic disturbances, and that's going to be something that we're going to come back to on a few occasions in this paper. It's very important. Hydraulics is the sort of flow of the water through the pipe and how that behaves. And meters, when they're produced and manufactured, the manufacturers will put them on their test rigs to make sure they work properly before they deliver them to us. And most of those test rigs are really sort of quite idealized situations. So they have what tends to be referred to as a sort of fully developed axisymmetric velocity profile, where the water flowing through the pipe is moving in well-defined streamlines, and there is a nice clear sort of structure to the profile. But obviously in real life, that rarely happens. We have bends, we have fittings, we have all kinds of disturbances in the pipes that mean that the flow can be distorted, whether that's distorted asymmetrically, as in that top right-hand picture, or in some cases where we get swirl, so the water is sort of corkscrewing along the pipe, as in that lower picture. And this can really affect the performance of our meters, as we shall see. So just want to talk about a little bit about DMA meters in particular. The UK was one of the first countries to adopt district meters or DMA meters, and they are critical in the UK in terms of our leakage reporting and management. Excuse me. The UK doesn't have fully universal metering across households, so we have to look at flows within districts, within discrete areas of the network, to try and understand what's happening around leakage, because we haven't got all the data from all the customers. So we tend to use what's referred to as a bottom-up leakage estimation method, where we're looking at the night flows. So we're trying to look at the flows into a district, into an area, over a defined period, usually an hour between sort of 2 and 4 a.m., where legitimate consumption is lowest. And then we can try and understand what's happening in terms of leakage within that part of the network. So that graph on the top right is a typical sort of DMA trace. So you can see that the flow rarely goes down to, or doesn't in that case go down to 0. But you can also see about halfway along that trace, that minimum flow goes up slightly, which could be indicative of a leak. But it could also be indicative of a problem with the meter. Which is again another reason to understand meter accuracy. In this case, it's fairly clear cut because the change is fairly sudden, but in other cases that change can be much more gradual, and it can be much more difficult to understand whether it is a metering problem or whether it is a genuine leakage problem. As I say, in the UK, we're one of the first countries to adopt district meters, so our stock is actually quite old in many cases. We did some work a couple of years ago with the industry, and a survey showed that there was meters that were still in service on district meters that were sort of more than 25 years old. Very few, but there were a lot that were more than, over half the stock was more than 10 years old or 10 years old and above. And the majority of the stocks was still mechanical turbine type meters, as in that top left picture. There is a move across to electromagnetic meters, as on the bottom right, particularly in terms of the benefits they offer from the stability of performance over the longer term. And probably in common with most areas, our district meters typically around 100 millimeters in size, so 80, 100, 150 are most common sizes. A few small ones and a few larger ones. Larger ones, particularly on where we have cascaded DMAs. So that's where one DMA is feeding another DMA. So I mentioned that a lot of our stock was quite old, and why is that important? Well, particularly for the turbine meters, we know they tend to age. We know that mechanical wear, they are mechanical devices, and wear happens within the bearings, within the components of the meter. That means their performance changes over time. And you can see in that top left graph some examples of meter curves. WRC does a lot of testing of meters, large meters and small meters. We have a large database of meter error data. So there's some example curves there that are fairly sort of typical. So a new meter will be, within specification, but as that meter ages, the performance gets poorer, the accuracy gets poorer. And what we will typically see is that the accuracy at the low flow rates will deteriorate more than at the higher flow rates. And this is obviously important when you're looking at night flows, because your night flows tend to happen at lower flow rates, almost by definition. So the part of the flow that you're most interested in is where the deterioration on the meter curve is happening. The problem we find is that it's not a sort of predictable or linear trend. For an individual meter, there's no way of looking at an individual meter and saying that meter is so old and it's of such type and therefore this is what its accuracy is going to be. It's much more of a probability-based scenario. So if you can see on that figure on the right, that shows the sort of proportions of meters in different age bands that are failing, as in giving very high errors, either at very low flows or at the low flow range or at the higher flow range. We tend to sort of say, well, around about the sort of 10 to 12 year mark is when you should be replacing district meters, because that's when your sort of failure rate is probably around about a third. So you've got a 30% chance of a meter failing. And the problem is you don't know which meters they are necessarily. So when you start looking at the economics of it, then for every 3 meters you're going to get one that is failed. So the economics sort of balance out, and the risk of poor performance and poor accuracy sort of balance out around that point. Certainly in that's our experience in UK terms. What's also important is to make sure that the meter is sized correctly, because then that will help mitigate some of that low flow drop off over time. So you want to try and avoid too much flow at low flow rates, because then that will lead to poorer accuracy, and certainly an increase in poorer accuracy, an increase in meter deterioration over the longer term, particularly on mechanical meters. And again, with mechanical meters, you don't want too much flow in the very high flow rate regions, because that will cause the meter to wear more rapidly. So there's a balance when you're looking at a DMA and trying to work out what size meter to put in, to make sure that you look at the flow rates that you're expecting in that area and size the meter accordingly. So on the right hand side, that little table is from a survey we did for a number of water companies, looking at how they specified a meter for a particular DMA, what size they would choose for that. And the most common, obviously, is looking at the sort of flows, modelling the flows, looking at the properties you've got in that DMA, modelling the flows and working out what the ideal size meter is. So not just putting in the meter that's exactly the same as the pipe diameter, because many pipes are oversized to cope with future expansion in the area, new housing developments, or it could be that pipes are oversized because what was originally in the area may have been sort of some commercial industrial properties that have downsized, or more water efficient processes, and therefore the pipe is still too big. So it's very important that as the DMA changes, that the size of the meter is reviewed, as the nature of the DMA, as the flows in the DMA, as the properties in the DMA are change, that you keep an eye on the size of the meter that you've got supplying that DMA, to make sure that the flows are still in an appropriate sort of regime with respect to the meter. Okay, So we mentioned hydraulics earlier and the importance of hydraulics. So just to illustrate that, the graph on the right shows a number of test data from a particular meter with this was a partially closed valve upstream of a turbine meter. So this was some tests that we did here a while ago, and you can see quite clearly that if you put the meter very close to the partially closed valve, then you're getting very significant errors, and as you move the meter further away from the valve, you get less errors. It's not always a predictable effect. You can see there that when you get to 5D, you're fairly close to the ideal situation on that particular meter. But we don't always find that, and particularly don't find that where there are disturbances that cause swirl. Then it's not necessarily such a sort of predictable pattern of behavior. And also you notice that in this particular instance, this meter tended to over record with respect to this bend, but other meters will under record, and you can get complications around how the asymmetry of the flow, whether that's because of the orientation, the plane of a bend or the plane of a valve, will affect meters in different ways. And we'll come back to this sort of theme slightly later. I'll explain why that's important. So though we know that poor hydraulics can lead to deterioration in performance, we can't always predict what that will be. The graph on the right shows some recent test data, actually, very recent test data. This is from an electromagnetic meter that we are testing. It's a 50 mil meter, and we've been testing meters here for, well, longer than I've been here, so well over 20, 30 years, and we've never had a particular problem testing electromagnetic meters. We install them correctly, we look at our earthing and grounding and so on, and follow the manufacturer's instructions. And we tested this meter recently, and we're getting that green line at the top, getting a consistent sort of 2% offset. And we thought, well, this isn't right. There's something going wrong here. And did some investigation. We had the meter manufacturer came along and had a look, and we did some various investigations, scratching our heads. And the conclusion was that it was probably an earthing effect, because we looked at this and we thought, well, what's going on here? The only thing that has changed in recent months around the sort of our test site is the fact that the railway line that runs relatively close, within about 50 meters of our test rig, has recently been electrified, and they turned the electrification on earlier this year. And that's the only change that we think can happen. And we think that has somehow affected the ground plane, or somehow affected brought in some sort of earth loop sort of problem. And we sort of went through the whole system, the meter, our logging system, our test rig, and we re-earthed everything with larger core cable, tied everything back to a common earth, and retested the meter, and lo and behold, that 2% had disappeared, and we were within the sort of specification, within the sort of range of results that we were expecting. So I think that illustrates that quite clearly, that with an electromagnetic meter, particularly on a district application, a DMA application, you really need to be very careful about the earthing, because obviously there's lots of power cables in the ground. You've got railways and other sort of potential sources that can affect set up fields with it, whether it's electrical fields within the earth, whether it's interference on the water that sets up some sort of electrical effect. I don't know. I'm not an electronics expert, but clearly there are effects like that can happen. So you have to take great care with the earthing, because 2% could be quite a misleading figure when you're looking at a water balancer across in a particular district. I mentioned environmental effects as well. And again, this is something that's not always very predictable. So you've got 3 graphs here which show examples of test work that we've done. The top left is an electromagnetic meter. So this was in a water bath, and we controlled the temperature of the water bath, so the ambient temperature on the outside of the meter. And we could see that the meter responded to that ambient temperature. So the blue line is the water bath temperature, the yellow dots is the meter response, and the difference between an isolated reference system and the meter, and the red line is the water temperature. And you can see quite clearly there that the output from the meter follows the same pattern as the water bath temperature, so the ambient temperature around the meter, not the temperature of the water going through it. Whereas if you look at the figure below, this is a mechanical meter. This was on the same test, same batch of tests. In exactly the same situation, the mechanical meter, the response of that follows, albeit inversely, the process water temperature, i.e. the temperature of the water that's going through the meter, not the ambient temperature. And on the top right, there's an electromagnetic meter that's doing the opposite. There's an electromagnetic meter that's responding to water temperature. So again, this is not necessarily a highly predictable effect. We know that some meters are affected by water temperature, some meters can be affected by ambient temperature. So when we're looking at water balances and looking at meter data, particularly where we're seeing seasonal effects between summer and winter, where you can get changes in water temperature of 10, 20 degrees, we would make an allowance typically of sort of 0.5 to 1% of that to be due to the effect of the water temperature or the ambient temperature on the meter itself, rather than necessarily a leakage effect. I'll pass back to Michael now.
Thank you, Andy. And I think what's really interesting, though some of this isn't predictable, as you say, we can take account for that in the uncertainties we ascribe to certain meters. So in Severn Trent, we've had a fairly aggressive program over the last few years of replacing our DMA meters, or being quite proactive. And we've replaced about 750 over the last 3 years. And just got an example of a couple of ones here. In the last 6 months or thereabouts, where we have replaced meters and the night line has gone down. In fact, one of these DMAs, it became operable. So our leakage guys have been looking for leaks that actually weren't there. And when we replaced the meter, we got a lower night line. Now, I've got to be honest, this isn't typical. As Andy explained, normally when you replace a meter, you will get a very, very similar result afterwards if you're just replacing it on age. And quite often, because of meter under registration, when you replace a meter, the night line will actually go up because now you'll start picking up flows that you hadn't previously picked up. And whether it goes up or down, to me, isn't overly important. The important thing is that you get to the truth. So you're putting your resources, your people that are trying to find the leaks in the right areas. And so you're prioritizing the right DMAs. So that's, I think, all that we really want to say on DMA leakage or DMA meters for the time being. We just move on to the next slide, Andy. I want to talk about large diameter meters. There is no kind of strict definition of what is a large diameter meter. For this presentation, and perhaps this presentation only, I'm going to describe a large diameter meter as anything that's greater than 250 mils, so a 10-inch and above. Now, most popular, or the place that we'll probably see them most frequently, is as a system input volume meter or a meter on the transmission mains. So again, if we move on, Andy. Okay, you hopefully all of us will be very familiar with this. So here is the IWA water balance, and as kind of Roland Lindberg suggested a few weeks ago in one of his webinars, the most important component is the system input volume, because if you get that wrong, then your whole balance is out of sequence, basically out of balance. So a 1% error on your system input volume has a really big effect compared to any other component in the water balance. Again, we can move on, Andy. Okay, so we looked at 4 water utility companies in the UK, and we asked them about how much of their system input volume went through meters that were 500 mils or larger. And essentially they said between 2/3 and 4/5 of the flow went through these large diameter meters. And I guess what I'm trying to kind of emphasize here is, even though relatively speaking, you've probably got very few system input volume meters compared to the thousands or hundreds of thousands of meters that you actually have in your system, but they play a disproportionate role. So I think in Severn Trent, for every one system input volume meter we have about 15 DMA meters. And so again, if you look at the larger ones, the larger system input volume meters, it's not unusual in certain companies or certain utilities that maybe just 10 meters actually supply, or the water goes through just 10 meters that goes to half their customers or half the network. So again, we don't have many system input volume meters generally in the network, but they play a really, really key role. If you'd like to move on, Andy. WRC did a survey of maybe half a dozen water companies about 5 years ago to look at what type of meters we use for large diameter metering and system input volume metering especially. And in the UK, you'll see that full bore electromagnetic meters came out on top by quite a distance. Almost 90%, 97% of meters in the UK, SIV meters, were electromagnetic meters. It's also worth saying that over the last few years, ultrasonic metering, clamp-on ultrasonic metering, has become more popular in the UK. And the reason being is 30 years ago, if we wanted to install a meter in the UK, and Alan Thomas, who's on the call, did lots of this for Severn Trent 30 years ago, what we'll do, we'll write a really nice letter to the customer saying, we're going to turn off your water for a few hours during the night because we want to install a flow meter. And that 30 years ago in England was very acceptable, to turn off the customer's water to do an engineering job. Now, the maturity of the water industry is different now in the UK, and that is no longer acceptable, and rightly so. We're a customer-focused business, and we've got to find ways of doing what we need to do, while making water always available. It's not acceptable to turn off the water now. And so clamp-on ultrasonics have become very popular because you can put clamp-on ultrasonics onto pipes. You don't have to turn the water off. You don't have to divert the water. You don't have to come up with expensive contingency plans. So for the remainder of my presentation, on my slides, we'll primarily look at electromagnetic meters and clamp-on ultrasonic meters. Andy, if you'd like to go on. Andy's already mentioned a little bit about electromagnetic meters, but for those who are not familiar, it's worth kind of stating how they work. So essentially, with an electromagnetic meter, you have electromagnetic coils that generate a magnetic field perpendicular to the direction of the fluid flow. And because water is a conductor of electricity moving within a magnetic field, a voltage is generated. Electrodes in the meter wall, they measure this voltage, which is directly proportional to the mean velocity of the water through the measurement section. And so therefore we can get a flow rate. We can work out how much water is going through that tube, through that pipe. And again, electromagnetics meters very popular for large diameter mains in the UK. Can we just move on, Andy, please? And again, really basic kind of description of clamp-on ultrasonic meters. And again, on the left-hand side, you'll see some pictures of electromagnetic meters. Sorry, not electromagnetic meters, clamp-on ultrasonic meters. So essentially, you have two transducers. They clamp onto the side of the pipe, and the transducer sends and receives ultrasonic pulses. Because we know the diameter of the pipe and the distance between the transducers, we can work out, or should I say, the meter can calculate the flow rate based on how quickly pulses are getting from one transducer to another. You can do this with a pair of transducers or several pairs of transducers and then average the flow rate. There's a few different setups. So you'll see on the left-hand side picture, you've got one transducer sending a signal to the other transducer, and they take turns in sending and receiving signals. On the right-hand side is what's probably more popular in the water industry, is where you'll see a V formation. So you have two transducers on the same pipe wall, and they send signals and they reflect it off the far pipe wall. Okay, so that's just a really basic introduction to electromagnetic meters and clamp-on ultrasonic meters. Now, in the brief, you'll have seen, those that read it, that I say that small meters or medium-sized meters, the meters that Andy's been talking about, work slightly differently to larger meters. And the reason I say that is because flow distortions travel further in larger diameter mains than smaller diameter mains, we believe. So what we've got here, you can see, is a computer generated hydraulics, or computer generated simulation, should I say. And the darker colors you'll see, so the dark orange, is basically higher velocity water. So velocity is the speed of water, okay, and is related to flow rate. So what you'll see in this computer simulation is on the darker orange is faster water, quicker water, speedier water. And what Andy showed right at the start was that an ideal profile is where you have fast water in the middle, and then gradually, in a very symmetrical way, you get lower and lower velocities. And when you go through a bend or through fittings, the flow profile can get distorted. And the effects of a disturbance dissipate quicker, we believe, in a smaller pipe. This is probably due to the ratio between the pipe diameter and the area within a pipe. And for larger pipes, the ratio between the area within the pipe and the pipe diameter is greater. So in a small pipe, if you're a molecule of water, as you come round a bend or as you go past a fitting, you may very quickly hit the sides of the pipe very, very quickly. And this distorted flow or this disturbed flow is dissipated. In a larger pipe, any single molecule of water takes a longer time to hit one pipe wall before it hits another pipe wall and then hits the other pipe wall again. And so this is why we think these distortions go on longer. So in this example, in this computer simulation, it's about 96 diameters or 160 meters before we get what we call an acceptable profile. Can we just go on to the next slide, please, Andy? The National Engineering Laboratory, which is a really good lab based just outside Glasgow in Scotland, has written that swirl can take over 100 pipe diameters to decay. Now, swirl is probably one of the worst distortions you can find. It goes on. In fact, there have been cases where swirl has persisted for over 500 pipe diameters before the profile returns to acceptably close to ideal. There's a really, really good case study of this in the American Waterworks Association Journal, and it's done by Dr. Dick Furness, who went down to Brazil. I don't have time to go all into the case study, but he looked at a 48-inch pipe in Brazil coming out of a pump station, and he found some really good evidence that swirl was still present in that pipe 200 diameters after the last disturbance. So what we're seeing in big pipes is that we get poor hydraulics, or we get distorted flows going on for possibly hundreds and hundreds of diameters. And that's why that's slightly different to when you're doing smaller meters or smaller pipes, where we think these disturbances or these distorted flows are sorted out a lot quicker. Andy, could we just move on to the next slide? Over the past 10 years, there has been a real good pieces of work done to look at looking at the accuracy of large diameter meters. So if you go back 10 years, there was very little independent literature about testing of large diameter meters. There has been some excellent work done by the University of Utah looking at this. Evaluation International, hats off. They've done at least 5 projects on large diameter mains, looking at the effects on electromagnetic meters, clamp-on meters, wetted ultrasonic meters that we'll come to a little bit. And again, real good hats off to Evaluation International, who are a non-for-profit organization. Andy Godley's WRC have done some work on this. Information and Performance Services, IMP Services, small company based in the Midlands of the UK, have done some excellent work on that. And as we look at these kind of 10 projects, myself and Andy have been involved in 8 of them. So we know a lot of the data. We know a lot of the testing that's been done. I put that there really for you if you ever want to watch YouTube again and pause this and look at some of the references that are there. So let's move on. Okay, because what we're really keen to do is share some of the learning and give you some really important takeaways that may help you as you design your network, as you upgrade your network, or as you come to try to work out meter uncertainties. So Evaluation International, as I said, did some really good work, and they did some like-for-like testings. They got a couple of ultrasonic meters that were 250 mil, and they got a couple of ultrasonic meters that went on 500 mil mains. Same meters, same manufacturers. They did the same for some electromagnetic meters, tested on 250 mil rig and then a 500 mil rig. And what we see is basically small is beautiful, is that we get better results on smaller mains than we do on larger mains. And that's quite important when you're trying to work out your uncertainty, or maybe you're deciding where you're going to put a meter. So maybe you've got a borehole and you've got two pipes coming out and they join a big main. Do you want to put 2 meters on the smaller pipes, or do you want to put 1 big meter on the larger main? And this suggests that actually you want to kind of put the meters on the smaller mains on there. Just have a quick look at the velocity as well. You'll see that as velocity increases, uncertainty goes down, or errors go down. If we go on to the next slide, Andy, because I want to talk about velocity now, and we've got an EMAG meter here. I tested it in various different scenarios, but what you'll see is velocity goes higher, the errors get closer together in most cases. The errors get lower. And what I kind of really want to emphasize here is that it seems to be really quite key to get to about 0.5 meters per second. That's how we measure velocity, 0.5 meters per second. If you get to that velocity, you've got to probably the best situation you can do. You can go a little bit higher, I guess, but you get very marginal gains after you get to 0.5. I guess that's what I'm trying to say. If we go on to the next slide, Andy, and this is emphasized from some testing that WRC did as well. And as you see, yes, after 0.5 meters per second, you don't really get much improvement. You could argue there's probably a little difference between 0.25 meters per second and 0.5 meters per second. And I take that on board. However, if I was writing a design manual for an installation team, I would probably say minimum velocity I want is 0.5. Part of that reason is sometimes engineers like to kind of take it down a little bit. So if I tell them 0.5, they might go for 0.4. Now, if I tell them 0.25, they might take me down a notch or two. So there's a bit of a safety margin there. But my recommendation would be to have your minimum velocity at 0.5 meters. And there's probably very little benefit of needing a higher velocity than that. Okay, Andy, if you'd like to move on again, please. So a question we get, and probably the most frequent question, is, how far do I need to be away from a disturbance? Now, a disturbance is anything that will distort the flow. Okay, so it can be a fitting, it can be a bend. And Evaluation International, on this rig that they use, this 500 mil rig up in Scotland at the NEL, they tested an EMAG meter, an electromagnetic meter, and they tested it 0 diameters down from the last disturbance. So that means you have your disturbance, you have your bend, or you have your valve that's partly open, and then you put the meter straight away after it. And then they did it 5 diameters down. So this would have been 2,500 mils down from the last disturbance. And then they did it 10 diameters down from the last disturbance. And what we see is that when you go from 0D to 5D, there's quite a difference. So the results at 5 diameters downstream from the disturbance are a lot better than at 0 diameters. So it appears that meters like to be socially distant. Now, when you get from 5 diameters down to 10 diameters, there's not really much difference. Okay, so a key takeaway we got for electromagnetic meters was, it's vital you get to 5Ds, but after that, again, it's marginal gains after that, very marginal gains. So getting to 5D is essential. Andy, if you would like to move on. Okay, so we then did some testing looking at ultrasonic meters, and IMP Services did this testing again at the NEL rig, at their 500 mil rig. And we tested quite a few ultrasonic meters. And what you've got in this graph is average errors from a number of ultrasonic meters. Now, the black bars is when we put the meter at 0 diameters, so right behind the disturbance. The red bars are 5 diameters downstream, and the 10 bars are 10 diameters downstream. And again, we've done it in different kind of velocity brackets there. Okay, a couple of things to point out here is that, this was a really distorted flow. So basically, we got a gate valve, we opened it only 25%, and then we put it around a double bend. or maybe vice versa around. But it was a really, really horrible flow profile. And what you'll see is that at any kind of velocity, is that at 0 diameters, the ultrasonics gave us the worst results. And then in most cases, all but one case, the best results were at 10 diameters. So if you look at this, getting further away is better. And again, you'll see the velocities, higher velocities is better, generally up to 0.5. So again, getting further away is better. Now, we'll show you some results now. We just want to hit the button, Andy. That WRC did for us last year. Okay, so they've made their main have some swirl in it. And what you'll see is the best results happen at 20 diameters down from the last disturbance. Then it's 5 diameters. And then you might be a little bit surprised, it's 0 diameters. And then it's 12 diameters. And then the worst case scenario is either at 2 diameters or 10 diameters, depending on what flow rate you're looking at. Now, this may be a little bit confusing because what we're seeing here is that further away is not always best. And Andy touched on this a little bit earlier, that actually, that with ultrasonics, it's a bit more difficult. Sometimes you can be really close to the disturbance and you get a really good result. And sometimes you can be far away, you cannot get quite as good results. But we're dealing with probabilities here. And so from the test data I've seen and from my experience, I would still recommend that you get your ultrasonic as far away as you can from the disturbance. Now, there's a few things that we can do to make sure that we optimize our ultrasonic performance, because in many cases, ultrasonics will be the optimal meter, especially in places where you cannot turn off the main and you need to put a meter in there. Andy, if you'd just like to go on to the next slide. And so there's a few guidelines that I think is really important that we should remember when installing clamp-on ultrasonics. First of all, let's get the highest velocity possible. Let's get as far away from the disturbance as possible. And let's make sure that when we install the ultrasonics that we have a really skilled technicians installing them. So when it comes to setting up transducers, millimeters matter. Millimeters matter. If you put that transducer in slightly the wrong place, you'll get a result that can be very different. Now, if I was deciding who I'd get to install my meters, my ultrasonic meters, I would get someone who takes pride in doing a really good job. I would get someone who is really fussy and really wants to do a good job, someone who's very particular, someone who's a bit of a perfectionist. What you don't want is someone who's a bit slapdash. And in slapdash, I guess it's an English term that we use, someone who wants to do a quick job and then gets on to the next job and doesn't really worry whether it's a good job or not. You know, you really need kind of a perfectionist putting on ultrasonic meters. And the other thing I think I'd like to add on is that more paths lead to more accuracy. And if you could just give us the, yeah. So what we'll see is here's a flow profile. You'll see that there's a higher flow rate, higher velocity on the right-hand side. We put one ultrasonic path, and we're probably going to get an under recording here because we missed the high flow rates. Now we put 2 paths on, we get a better picture. And if you want to hit the button again, Andy, we put a few more paths on, and there we get a better picture on that. If we move on, we did an experiment in Severn Trent on a large main, 600mm main. We had asymmetrical flow profile, I believe, in the main, or maybe even some swirl in the main. We put on 4 ultrasonics, and we got 4 different answers. 2 were quite close to the average, and then 2 were quite different. And so this kind of, for me, was an example of, on larger mains, especially if they're strategic mains, you would want to put on quite a number of paths to increase that confidence. And this, we put these on 100 diameters or more than 100 diameters from the last disturbance. Andy, if you'd like to. There are a couple of alternative technologies that are worth mentioning, and we've installed both of these in Severn Trent fairly recently. So one is wetted ultrasonics, and you see that on the left-hand side, where you put transducers that go slightly into the main. That means that they don't have to worry about pipe wall thickness, which can sometimes also cause errors, and they actually see what's happening in the main. So again, we've installed a couple of them in Severn Trent, and again, lots of testing's been done on them, And again, that's something that I would recommend as a good product to consider using. Another product well worth consider using, and again, we've used it in Severn Trent, and we're putting them on our transmission main, is a multi-point sensor. And this goes into the main. It has several different points, and it picks up the different velocities you've got on there. So again, helps give you a picture of what's happening in there. Again, they're well worth looking at. Evaluation International, University of Utah have done some testing on these meters. Andy, I think it's back over to you now.
Okay, thank you, Michael. So we've given a run through there of lots of different things that can affect both large meters, the DMA meters, and so large meters and smaller meters, DMA meters and system input meters, and I guess lots of things that can affect the accuracy of the meters in different ways. And I think one of the points that hopefully has come across is that this is not necessarily a predictable phenomenon. There's all these things happening, but they're all independent. They all behave in different ways. They all affect different meters in different ways, and it's not always possible to predict that effect. So how do we use that then? Well, we use an approach around uncertainty. So uncertainty is the statistical quantification of accuracy. So it's a statistical technique. The methodology is well defined by international standards, in particular ISO Guide 98 Part 3, which is also known as the GUM, the Guide to Uncertainty in Measurement. And we use that, and we have to identify all and try and quantify all those sources of uncertainty that can affect our meter. And you've seen quite a number of those already today. And there is lots more published information, and there are test reports published on individual meters. And you know, there is a lot of information out there. And we use that information to build an uncertainty budget for each meter. And we would do this for each individual meter, and uncertainty budgets can take several different forms, but there's an example there at the bottom on the left. So all the different components of uncertainty, so that the sort of underlying basic performance of the meter that comes from the manufacturer's specification. In this example, we know that there's an upstream bend, so there's a component due to the hydraulic conditions. We don't necessarily know how that bend is affecting that meter, but we know it's having some effect, and we know sort of approximately the magnitude of that effect, so we can allow for that. We can look at things like aging. We know how old the meter is. We can make an allowance for that. And all the different parameters we can make allowances for based on what published information we've got from that. And we use the statistical techniques around combining the components, those components in quadrature, so root, mean, square, sum, to work out what that overall uncertainty is. And then we can look at that at different confidence levels. So one would normally do it at a standard confidence level, 65% confidence level. But then if you want to look at a 95% confidence level, then you effectively double that by multiplying by the coverage factor, which is around 2 for 95% confidence factors. So we can build up uncertainty budgets for all our meters that take into account all these unknowns, all these sources of potential error. As I say, we don't know whether they're happening. We're in the world of probability here rather than absolutes. And we can find out what our expected uncertainty for each of the meters in our system are. And then when we're looking at combining data from different meters, so for example, we're doing a balance, we're doing a balance over a discrete, water balance over a discrete area of the network, we can then combine the uncertainties from the individual meters to build up that balance, and we can add that balance in. So examples on the right there, you can see in the top graph, the dark blue line. So this was a trunk mains balance. So we've got a number of flows going into this discrete area, which happens to be a part of a trunk main. There's a meter on the inlet, and then there's lots of outlet meters. So there's meters to DMAs, meters to industrial customers, various other meters within this network. When we add up, or when we subtract everything that's going out of this part of the network from the amount of volume that's going into the network, then we get that dark blue trace, i.e. we get some residual, we get something that suggests that there's more water going into that part of the network than is coming out, which would suggest leakage. But what we can then do is map all the uncertainties of all those meters and combine all those uncertainties of all those meters onto that residual. And we see that the overall uncertainty of the residual falls, that there's a possibility there that that residual is actually zero when you take into account the meter uncertainty. So there's a possibility there that in that case, that residual could just be an artifact of the meter errors within that system, and that loss could not necessarily be real. It could be, as I say, an artifact of the meter errors and the meter uncertainty. If you compare that with the graph at the bottom there, exactly the same. This is a different trunk main area. Again, we've taken off all the outputs from the input, more than one input in this case, looked at all the uncertainties, mapped those uncertainties onto that residual, that dark blue line, which is potentially leakage. And we can see that there, even allowing for meter uncertainty, there is still a residual. That line, that band defined by the uncertainty bands never goes down to absolutely zero, which suggests there is a real loss in that network somewhere. So when we're doing our planning in terms of our leakage crews and deciding where to prioritize and where to go and look for leakage, there's a higher probability that if they concentrate on the area in the lower graph, that they will find some real losses than in the top graph, or the area that's represented by the top graph, if you like. Now, this is not a guarantee. As I say, we're in the world of probability here, but this is looking at sort of risk and looking at likelihoods as to where you want to spend your money in terms of your leakage crews. Then, there's probably gain to be had by looking at the area in the lower graph than in the upper graph. I just want to touch on verification, because we've talked a lot about meter uncertainty and the fact that there are lots of things that can affect our meters. And most of the water utilities in the UK have some program in place to verify many of their larger meters, as we've sort of tried to emphasize, particularly the large meters, and Michael showed in his slide, are very critical to our water balance. So we need to have confidence in those meters. And so we put in place, most water utilities have got in place a verification program, and this can, say it can be a regulatory requirement, it's often an auditory requirement, or it can be just where you think that there's some problem with the meter that you want to go and try and see whether things in that meter have changed, or it could be acceptance tests. But all these different reasons for doing verification really link to us having confidence in the data we get from that meter. So we've done a program of work recently to try and identify how you develop a strategy in relation to a verification program. If you've got lots of meters, lots of large meters within your meter park, that you need to sort of think, well, I've only got so much to spend on this verification program. Where do I focus my budget? How do I develop a strategy that will give me the most best results for the money I've got available? And we can look at the risk factors associated with those meters. How significant is this meter in terms of how much volume it's recording? In my water balance, and a more significant meter, you may conclude it's got a higher risk. And you can look at all the other factors. This is a very old meter. It's more likely to be having errors. It's a type of meter that I've had problems with before, or it's an individual meter that I've had problems with before. So you can look at all these risk factors and you can balance them up. You can look at what the risk of that poor measurement from that meter is, or conversely, the other side of that coin really is how much confidence do I need in that data? How sure do I need to be in that particular meter? So you can balance these round, and you can use those to define a strategy around verification in terms of the frequency with which you verify meters and the methods that you use I just want to touch on the methods that you use, because we have a lot of different methods for meter verification in the UK, particularly with our water mains meters, both our DMA meters and our trunk mains meters. They will be verified in situ. It's very rare to take a meter out of service to test it on a test rig, partly because of the disruption to the downstream customers, and partly to the costs of actually extracting a meter, particularly a very large meter. So we have a number of different ways of verifying meters, whether that's through doing independent flow tests, through something like a clamp-on, ultrasonic, which Michael's talked about, an insertion meter, or there are other more advanced methods like thermodynamic testing, where you've got a pumped flow, tracer methods, and so on. So lots of different methods. Also, the electromagnetic meter manufacturers, particularly Siemens and ABB, provide us with electronic verification tools, which I understand are quite well used in the UK, but perhaps less used in other parts of the world. But the important thing to remember about electronic verification is that it's not actually giving you an independent measurement of the flow, as the other techniques shown there are. What it's doing is looking at the meter electronics, and trying to diagnose whether those meter electronics are behaving as they should, as they were when the meter was performed. That all the circuitry within the meter electronics are still behaving as they were when the meter's manufactured. And the sort of logical consequence of that is that if the electronics are performing correctly, then the meter is still measuring correctly. There's a couple of caveats around that, particularly around hydraulic disturbances. The meter may still be performing and measuring electronically well, but if you've got a poor velocity profile in there may be effects from the hydraulics that electronic verification will not be picking up. One of the problems we've got, though, one of the challenges we have with all these techniques is that the verification technique is likely to be inherently less accurate than the meter that we're doing the tests. So again, we have to go back to our uncertainty balances. We have to build an uncertainty balance for the meter, the installed meter, and also the verification technique. And then we can use some statistical techniques to look at how significant that difference is between the verification result and the meter result, to know whether there's a problem with the meter, or the probability of there being a problem with the meter, or the probability that is just within the sort of uncertainty limits of the two methods that we're measuring.
Thank you, Andy. We're less than 60 seconds away till questions, so get your questions in. I see Joe Parker's already got one up there. Okay. All right, so there's a number of guidance documents that are available that you can look at. NEL have done a brilliant one a few years ago, quite a few documents there. Evaluation International, and I don't know of any organization over the last 10 years who've done more to test large diameter meters than Evaluation International. They have got an installation guidance document coming out soon, or it's being written up now. So again, you may want to contact them, and they're going to be looking at a lot of the testing that's been done over the last 10 years and turning that into an installation guidance. There's various international standards. WRC have a training course that Andy leads that was created with the help of Northumbrian Water, Severn Trent Water, Welsh Water a few years ago. I've been on it, very good. And also online, Chrome Online Academy is again very good, good graphics to understand metering and hydraulics. Just the next slide, Andy, and then it is questions after that. We're still looking to do further research. We still, as you see from today, we've learned a lot over the last 10 years. There's still lots of things that we need to understand. And we really want to look at large meters, so 1,000 mil meters. As we say, these meters are disproportionately important to the water balance. I know one UK company, about half their system import volume goes through about 8 or 9, maybe even less than that, 1,000 mil meters or bigger. So really, really important. As we know, there's a difference between 250 mil and 500 mil. Performance-wise, we want to know there's a difference between 500 mil and 1,000 mil. That's important for uncertainty. That's important for installation guidance. There's support for the project in the UK. There's interest in Australia. I think there may be a bit of interest in the USA. If you're interested in this joint venture, because we're trying to put together a joint venture, if you could contact me, you've got my email address down there. By the 22nd of June, And we're trying to really make this into an international project where we can all benefit from it, because we know we've got large mains in all continents of the world, all populated continents of the world anyway. So that's all I kind of really wanted to say on that. Happy to take any questions. It looks like we've already got a few on there. So just going to go try. I think Joe Parker had the first one. Okay, so she says she's working for a water company who's looking to install full bore permanent ultrasonic meters as opposed to bolt-on, the ones that we've talked about today. How do these compare with electromagnetic meters? Andy, do you want to take that first? Or if not, I've got a few views on it.
The permanent permanent ultrasonic meters. So this is a sort of wetted transducer type. Obviously, you've got less sources of uncertainty there. You've got a well-defined path. You've got none of the problems of trying to get an ultrasonic signal through a pipe wall. And they can be extremely accurate. I know the oil and gas industry use permanent ultrasonics for fiscal metering, usually multi-path devices. So you can have very high accuracy and probably perform to similar standards to electromagnetic meters. Michael, what are your...
Yeah, just to add to that, Andy, I think one of the questions would be kind of what is the size? So we know of some ultrasonic meters that have been used at DMAs, these full bore ultrasonic, and I believe, if I remember correctly, Andy, we tested some a few years ago. They gave pretty good results. They gave pretty good results. So there's a couple of water companies in the UK that have used these full bore ultrasonic meters for their DMA meters, and yeah, they got good results out of them. Okay, let's see what other questions we've got. If that doesn't answer it, Joe, come back to us. Okay, if that wasn't specific enough. Okay, so here we go. Aside from an age error correlation analysis for mechanical meters, have you considered evaluating whether the throughput and the meter error have a relationship? Andy, that's one for you.
Okay, so when we've looked at mechanical meters, we've tried different correlations with throughput and age. What we find with particularly with the district meters, the district and perhaps industrial revenue meter size, the size is sort of like 50, 80, 100, 150 mil sizes. What we find it quite difficult to get hold of in terms of data is the actual throughput of the meter in terms of the total volume it's recorded. A lot of these meters are installed for quite a long time. They can go what we call clocking, i.e. they can go round from the maximum registered value back to zero and start off again. So we've got some uncertainty on that, particularly with some of the lower mileage meters that we see. We question whether they're clocked or not. We think it ought to be. We think that the correlation ought to be more consumption related or recorded consumption related than age specifically. But when we've done the modelling, we actually find that age is a better variable. It's an easier variable for people to understand in some ways, which makes it quite good in terms of getting a message out to say you need to replace this meter every 12 years or whatever. It can go on to a sort of like a schedule, and it makes it easier for people to plan rather than saying we need to replace this meter when it's recorded 500,000 cubes or whatever. We've done a lot more work on small meters in this on this, and again we found age to be a better correlation at a statistical level, and I think that's probably the important point, is that we are using age in some ways as a surrogate for consumption, and that many of the meters, if they've been properly sized, similar meters on similar DMAs will see similar amounts of consumption over similar times. So in some ways age is a surrogate for consumption, but we've generally found it more successful trying to do correlations off age, partly because the data is often clearer in many ways. I don't know whether you've got anything to add to that, Michael.
No, I think that's a really good and complete answer, Andy. And as you say, we know mechanical meters are going to wear, aren't they? They've got more wearing parts than perhaps the clamp-on ultrasonics or the electromagnetic meters. With something like a clamp-on ultrasonic, you need to make sure it's still got a good connection after a few years. And again, there's been a really, I think there's been a real good improvement on the clamp-on ultrasonics over the last few years on how well they perform, and also ensuring that you have the right pads or whatever connection you need onto the main on that. Someone's asked about consider sharing a copy of the presentation. The presentation will be on YouTube. So Gary normally puts them up very quickly within a day. So again, what we did deliberately, we made some of our things a little bit wordy. So you can go back. And again, we put quite a few of the web addresses on there. So again, if you want to contact the people who have provided the data, because again, they've been very generous to myself and Andy in allowing us to use some examples, please do. Okay, I'm just seeing if we've got any other more messages on there. Okay. Could you tell us which part is the most latest insight in this 2 years, or what is most interested part right for you now? Okay, what are we most interested in right now, or what do we want to learn? I think probably a few things that we have learned over the last few years has been that get your velocity to 0.5 meters per second, get at least 5 diameters downstream from a disturbance if you're an electromagnetic meter. If you're an ultrasonic, get even further downstream than that. The other thing that's been really quite interesting, and we only put one slide on it, is the alternative technologies out there. So there's wetted ultrasonic meters now, although I guess they've been around for a while, but there are companies that are providing wetted ultrasonic meters, which is great because you don't have to worry about the pipe wall thickness, which can vary around the main. You don't have to worry about if it's got a lining or not, which can sometimes be a little bit difficult to know. Again, you've got this multi-point sensor that we're putting into the mains, and we put one in fairly recently in Warwickshire in the UK, and we've got other ones that we're installing on there. So what I'm saying is that I think there's a lot of technologies that now mean you can install meters without having to turn off the main. With all that said, I think most people will say the best meter is, if you can, is still the electromagnetic meter. If cost and time and the cost isn't so much buying the meter, the cost is having to divert mains and contingency plans and things like that. I think what's really interesting for me, Nobu, is what we're going to do next will be kind of this research that we've got, is what happens at 1,000 mils. Now, we couldn't find any research, any independent testing of the accuracy of large diameter meters at 1,000 mils at 40 inches. And we know that lots of companies around the world, lots of utilities around the world do use meters of that size. So again, would love to do that testing and get some answers there on that. Andy, anything that you're kind of really interested that you think we're really keen to learn over the next few years?
Well, I think you're right. As we get bigger meters, will be good. I think one of the things that we've been, in the last 2 years, in terms of some of the work that we've been doing, has been around what we were talking about around the uncertainty balances, particularly. So in the UK over the last couple of years, there's been a big increase in interest in doing in trunk mains losses. So we've done lots of work over many years on at the district level, but the trunk mains have been quite neglected in some ways in terms of water balance and leakage. So some of the methodologies we've developed around doing trunk mains balances with taking into account meter errors, meter uncertainty. I think that's been quite interesting, particularly on terms of helping prioritise areas for investigation for leakage, I say, at that level, because it's not necessarily that straightforward. But yeah, so I would just add that in terms of last couple of years.
Yeah, we've got another question here that I'd really like your input on, Andy. It's talking about long-term maintenance of strap-on, clamp-on
Yeah.
ultrasonic meters.
Yeah.
Now, we know in the past, if you're not careful, so the ultrasonic meters, the transducers does not go straight onto the main. You normally have a gel, or you have a pad there that goes in between. And one of the problems they've had historically, so maybe going back 10, 20 years, is that you put the gel on and the gel would dry out, and then you wouldn't get as good a connection on there. And so part of the maintenance, if you're using the gel, is that you'd have to go back fairly frequently and put it on there. Now, most of the manufacturers have moved towards kind of using a pad, which I believe can stay there, and you don't really have to do any maintenance of it. I don't know what your thoughts are, Andy, on that, or your understanding of that.
Yeah, I mean, I try and get the message out that I don't think there's no such thing as a fit and forget meter, despite what many of the manufacturers will tell you. All meters will need some maintenance over their lifetime. Now, that could just be inspecting them and making sure that that everything's hunky dory. But there can be corrosion on terminal boxes, on cables. We've certainly seen issues of that. A lot of meters, certainly again back in the UK, meters are in chambers. They're not necessarily in the best environment. If you're going back to district meter, you might be in a chamber at the side of the road where you're getting road runoff, so you're getting water contaminated with salt or diesel or whatever. So there's lots of things that can happen that will cause that meter to sort of deteriorate. You can get damage to cables, rodents, or diggers. So there's no such thing as a forget meter. So you should be going out and inspecting meters, on a reasonably regular basis. And in terms of ultrasonics, especially the strap-on ultrasonics, as Michael said, that coupling is very critical. If you're in a location where there may be vibration, that may affect the sort of security of the fixings on the transducers. It may, for severe vibration, if you're on the side of a road with a lot of heavy traffic, you may get the transducers may be even sort of displaced slightly. If the surface of the pipe corrodes, then again that can have an effect on the location of those transducers. So I think it's important that whatever type of meter you've got, then it's not fit and forget. You do go out and inspect it. You do go out and check that everything's, there hasn't been any deterioration on the meter or the environment that can be affecting that meter.
And I think probably something just to add is often when we look at meter areas, so as you mentioned right at the start, Andy, is to emphasize that often the problem is telemetry. So if you're getting a funny result back at your control center, often it's a telemetry problem, and that's what needs to be investigated on there. So often we say, oh, the meter's not working. Actually, it's trying to get the signal from the meter down to the control room is often the problem there. And again, probably another thing worth doing is about kind of the validation. So a real simple way that we validate the meter, and this is as basic as you can get it, we look at the flow of that meter 1 month and we compare it to the flow of that next month. And because we've got quite a few years of data, we can quickly identify if one of the meters looks like it's giving a rogue signal. And that's when we then call up the treatment works and say, look, what's happened here? And they can say, oh, that main's out of commission, or et cetera, et cetera. And again, if you're able to do a flow balance, so compare your flow meter to perhaps a flow meter or meters upstream or downstream, and if you can automate that's really good, because again, you've got an alert system or that will tell you actually there's potentially a problem there, and again you can then go to that. And again, you may want to automate it, or maybe you'll just say, okay, every 3 months, every 6 months, we'll do a very basic flow balance, compare this meter to this meter, and as long as they're within 2%, 5%, whatever the parameter you feel is right, we're going to be happy with that.
Okay, thank you very much, Michael and Andy. I think you've answered all the questions now. Very interesting presentation, and definitely a lot of food for thought there, I think. So there's probably a lot of people sat at home now thinking about all of the meters they've installed in the past and wondering how accurate they really are.
Gary, just on one final very quick point on that.
Yeah.
Because I was thinking about this morning, because sometimes the more you learn, the more you get worried about things. So it's like,
Yeah.
oh gosh, thought my network was perfect. I think the IWA water balance gives us a way that if we become a bit more uncertain or a bit more unsure, we can always increase the uncertainty to take account of that. And in some cases in Severn Trent, as we've learned a little bit more, we said, oh, I'm not as sure as I would be about that. And actually, we've increased our uncertainty on certain things. So again, the IWA water balance 20 years ago, Alan Lambert, ahead of his time in many ways, we do have a method of dealing with that in many ways. Obviously, the best thing is to kind of make sure our meters are all working perfectly. They're in fantastic positions. But in the real world, we know sometimes we can't do anything about that. And probably just increasing the uncertainty is perhaps the best thing we can do in the short term.
Right. Okay. Well, thanks once again to both of you. And with that, I think we'll finish the webinar here.
Thank you.
Okay.